Hey guys, so here's a video I promised. Well, I didn't really promise, I just told you I'd do it. But anyway, so talking about friction and frictional forces. So we'll talk a little bit and then I'm going to work through three different examples. Um, so the one thing is I can't really show you an algorithm for solving every frictional force, and this just goes for physics in general. Instead, we just need to work with the principles that we know. And so we're going to be dealing mostly with just Newton's laws. Either his first law, the sum of the forces is zero, so there's no acceleration, or his second law, trying to determine the acceleration with the net force. And now we're just throwing the friction force into it. So just to recap, the frictional force, sorry, let's do this. So we'll write it like they do on the equation sheet. The frictional force, the magnitude of it is going to be less than or equal to the coefficient of friction times the normal force. All right. My handwriting is not so great with this, but oh well. That is the coefficient of friction. And what's that measure? So it's just a coefficient of friction. Seems like it's gotten worse. I think I'm out of practice. All right, the coefficient of friction. What that is that's just a measure of the friction between surfaces. Friction between two surfaces. So what we can do is we can test surfaces, and then we get a number then. And then the normal is, it's part of the weight. That coefficient of friction, though, I mean, if you go out and Google coefficient of friction table, then we can pull up a table that has all of these different, let's see what we can see. Oh, let's go back. There's an engineering toolbox. Let's see what this thing has. So here's a bunch of static friction, clean and dry. So you could look it up and you could say, okay, well, look, I got a brick sliding across a wood beam. The coefficient of friction of static friction is going to be 0.6, versus cast iron on cast iron. Look at that, 1.1. See, so theoretically we can't go above 1, but yeah, sometimes you can, especially if it's really smooth and it's the same material. And then you go down, so you see how it works. They just test it out and we get this number, and so that number always applies. So it depends on the surface, but then it also depends on the normal force. And so that normal force is a lot of times if we're dealing with just a horizontal surface, well, then the normal force is just going to be a reaction to the weight. So we have a horizontal surface, you have some object sitting on it, so you're going to have some weight acting downward. And since that weight acts downward and pushes against the floor by Newton's third law, the floor pushes back. And in this case, it pushes actually straight up. I'm drawing terribly. And so in this case, on a horizontal surface, we know that the normal force is equal to the force of gravity, and the force of gravity is just mg. So we know that everything's good. We can just calculate it. It's dependent upon the mass. The more massive the object, the more force of friction I'm going to have. All right, but what about when it's not on a horizontal surface? Well, so if we're looking at an inclined plane, then we still have some weight pushing down onto the surface, but it's pushing at an angle, and my normal force pushes perpendicular. And so it pushes up like this. And so that normal force is not equal to the force of gravity. Instead, it's going to be equal to some component over here. So we're going to have to go in and we're going to have to draw our triangle to get this component right here. And that's force of G in the Y direction. So we'll use some trig using this angle. And then we'll also have this one. But anyway, we're just talking about the normal force. So the normal force for an inclined plane is equal to the force of G in the Y direction. So the normal is equal to the force of gravity in the Y direction, just the component of it. And so in this case, if this was theta, then FGY, the normal would be equal to FG cosine theta. And then FG is just mg, so we get mg cosine theta. So in general, when you set up your diagram like this, that's what we'll be dealing with. So now it's just applying it. So that's our concept. That's our friction. Okay. So let's look at an example. So we have a crate sitting on a horizontal surface. The coefficient of static friction is 0.45. What force must be applied to the crate to just begin to make it move? So it's not moving. Hold on, I lost my little cursor. There it is. Okay. All right. So let's just draw a little picture. So we have a horizontal surface. That's the best line I've ever drawn in the software. And then we have a box sitting on it. Okay, so we're going to have some weight, the force of gravity acting down, and then we'll also have the normal force coming up. And so you should recognize right away that this box is not moving up and down. So the net force in the y direction is equal to 0. Or we could just say that the normal is going to be equal to Fg. And Fg is mg. So the normal force is going to be mg. So I just write that down so I know. Okay, so now we know that the coefficient of static friction is 0.45. We know the mass is 13 kilograms. And what we want to know is we want to know if I apply a force in this direction, or whichever direction. So I want to apply a force such that it overcomes the static frictional force. So remember, the static friction, there's a maximum, and once you reach that maximum, it will break free and start to move. So what I want to know is, when is this force equal to this force, to the maximum? And so we want to know the force such that it's greater than or equal to the force of static friction. And then turning back to our definition, recall that the force of static friction is going to be the coefficient of friction times the normal force. So now we can just start substituting. So my force applied would be greater than or equal to the coefficient of static friction times the normal force. And our normal force is Fg, so let's substitute that. So we get the coefficient of static friction times mg. I'm sorry, so Fg, we would do Fg, and then since Fg is mg, we can substitute it in, and that's it. Okay, so now it's just calculating. The normal force is greater than or equal to the coefficient, 0. I know that looks like a 9, it's a 4 or 5, times the mass, which is 13, times g, which is 9.8. And that would be my force. I'm not going to calculate it. So if my force is greater than or equal to this, that's the maximum static frictional force, then the box will start to move. Okay? All right. One thing you may want to do is just try to do these before I do them. Okay, so a worker is pushing an 11.2 kilogram box across a horizontal floor with constant speed. The coefficient of kinetic friction between the box and the floor is 0.2. What horizontal force must be applied to maintain the same velocity? Okay, so now we have a box that's moving. But again, we'll just draw it. So we have a surface here with a box. So we have some weight coming down. All right, so my horizontal lines are getting better. My vertical still are pretty terrible. Force of gravity, and then your opposite force would be the normal. So again, we know that the normal is equal to the force of gravity, which is equal to mg. So the normal is equal to mg. We know the mass. The mass is going to be 11.2. We have a velocity of 3.50 meters per second. And we know the coefficient of kinetic friction. So we put a little k to show that it's kinetic, 0.20. Okay, so the key here is this part, this constant speed. Since it's constant speed, I know that the acceleration is 0. which implies that the net force is 0. So what that means is that whatever force I apply in this direction has to be equal to the kinetic frictional force. So the picture actually looks exactly the same as this one, except now we're talking about kinetic friction because we have some velocity. This box is actually moving, so it's kinetic friction. So what I know is that the force that I apply has to be equal to the kinetic frictional force. And so again, working with our equation for friction, it's equal to the coefficient of kinetic friction times the normal force. Do not skip steps here. We want to see that before you, and then substitute. So you need to have some derivation of normal force. So it's going to be the coefficient of kinetic friction times the force of gravity, or the weight, which is equal to mg. Kinetic friction times mg. And I'll leave it there. You would just plug in these numbers. So the velocity we didn't need. They give it to us because then you can say, well, what would happen if you stop pushing it? What's going to happen to the block? How far would it fall? So we can find acceleration and use Newton's second law. I wanted to do one more example though for you before this video got too long. And so now we're going to deal with an inclined plane. So we have a box sitting on an inclined plane. So let's just draw an inclined plane. This is at 12 degrees. We have a box sitting here. So this is all about drawing the diagram correctly. You do that, everything else is fine. So again, we have the force of gravity acting straight down. And then you have a normal acting up, perpendicular to the plane. So that's my normal force. Now my normal is not equal to the force of gravity. Instead, we're going to have to draw in those components. So we need to come straight down, or well, straight down opposite of the normal is what I mean. And that would be my force of gravity in the y direction. And then we would go parallel to the plane. So this would be the force of gravity in the x direction. And then my angle is right there. That's the 12 degrees. Okay, so now we can do some stuff. So now I can see that the normal is equal to the force of gravity in the y direction. And let's go ahead and we can calculate that. The force of gravity in the y direction, since it's next to the angle, it's going to be Fg cosine theta. All right, so we want to know the frictional force that's holding the box in place. Okay, so what we have here is we're going to have a static frictional force that acts up the plane. And the static frictional force is going to be equivalent to this one down here. So let me just highlight that. This one is going to be equivalent to this one because they're both acting parallel to the plane. In fact, I could just draw this up here, you know, it would go right here. That would be my Fg in the x direction. So let me write that down. So my static frictional force is equal to the force of G in the x direction. Okay, so let's see. How would we calculate the force of G in the x direction? Well, it's opposite. That would be Fg sine theta. So let's go ahead and substitute. So first we'll change the force of static friction. The force of static friction is the coefficient of static friction. What do we want though? I'm sorry. We just want the force. So we want to know what this force is. So we don't even have to do this. Let's scratch that out. We don't need to do that. We just want the force. So the force of static friction would be F of G in the x direction, which is Fg sine theta. And then so the force of static friction would be the force of gravity is mg sine theta. And then you just plug in your numbers. and you're done with that. But then the second one is like, what's the maximum angle that the plane can have before it begins to slide? So now we would want to know, what angle. So using the same equation, this one, you would substitute and calculate for the first part. But now I'm going to keep working, because what I want to do is I want to determine what is the angle, the max angle. So the force of static friction, that would be the coefficient times the normal. The coefficient times the normal force is equal to mg sine theta. And then the normal force is going to be Fg in the y direction. So the normal force is equal to Fg cosine theta. So we can substitute that. The coefficient of kinetic friction times Fg cosine theta equals mg sine theta. But here's the thing, this is mg, that's the force of gravity, so these things cancel out, they divide off. And so I get the coefficient of kinetic energy of kinetic friction times cosine theta equals sine theta. Now we need to get the thetas on the same side, so you would get this equals sine theta divided by cosine theta. And sine divided by cosine is tangent. So we end up with arctan of the coefficient is equal to the max angle. This part I'll talk about in class if I haven't already. Why that's equal to tangent theta. All right, so I know this last part got a little weird, but just know, you just start with you just work with the basic principles, okay? You're never going to memorize every single step. You just work piece by piece and you start putting it together. It's very much of a puzzle, but one that you can do, okay? It just takes some practice, going step by step. If you get to a point where you don't know the next step, then you just ask me, you come see me, and I'll gladly tell you the next step and get you unstuck so that you can continue, okay? You can't just leave it blank and just say, I don't get any of it. I can't really help you in that case. All right, so yeah, give it a go. We'll see where we are next class.